Welcome back. I'm going to actually write some code in this video, not that much. So what I'm doing now, welcome. I made a few introductory videos, covered some background about neural networks and why they exist and where I'm trying to go with this. And in this video, I'm going to actually begin to write the code for a simple JavaScript neural network library. Now, I've actually already done this. It exists here at this repository, GitHub shiftman/neural-network-p5. I'm designing this library to be used with a set of P5.js examples with a library, a JavaScript library called P5. Although ultimately this library stands alone on itself, by itself. You don't have to use it with just P5. So before I can write the code, let me come over here to the whiteboard, and this is where I last left off talking about how the general structure of a neural network library works, of a neural network system works. And so what I need to do here is when in the code I create a neural network, I want to create three things. I want to create an input layer. I want to create a hidden layer, and I want to create an output layer. So when I create a new, the way I want to design this library is I want to say new neural network, and I want to give it, can you see this? I think you can. I want to give it three arguments. The number of input neurons, let's just use the word neurons, the number of hidden neurons, and the number of output neurons. So I'm doing something which I typically don't do, which is usually I like to have a specific problem that I'm trying to solve and like write the code for that problem. And in here, the problem that I want to solve is I want to make a generic, kind of useful library that can be used in a bunch of different contexts. So I don't know what those numbers are going to be. I don't know what the data is. I'm just kind of working on the skeleton, the structure of the library before I start to apply it to things. So let's just make up some numbers. Let's say there's going to be 3 input neurons, 4 hidden neurons, and 2 output neurons. What this means now is in a feed-forward neural network, there are 3 inputs. We could imagine, again, I'm using the kind of classic example of guessing the price of a house. This could be number of bedrooms, number of bathrooms, square footage. So those are like 3 parameters of a house. These will connect to 1, 2, 3, 4 hidden neurons. So this is the input layer. This is the hidden layer. And then I'm kind of running out of space here. There will be 2 outputs. And then this is the output layer. So this is the configuration. The idea of and so what I'm building here is what's known as, this is a multi-layered perceptron. These are individual perceptron units, essentially, that have multiple layers. And it also is another important term that I want to add here is I want to create a fully connected network. And now there are variations to this that we might see in future examples, but the idea of a fully connected network is that every input is connected to every hidden is connected to every output. So I can draw all those connections. And it's not so many that if I were doing some kind of post-production, I would speed this up, but I'm going to just draw this web of all these connections. So every input is connected to every hidden, and every hidden is connected to every output. Whoa, oops, I messed this up, but I'll get it eventually. There we go. Right, so you can see that every node is connected to every node in the next layer. So the idea is that those 3 inputs come in, the data feeds forward, and those 2 outputs come out. So this is the structure. Now, we have to get into a lot of details here. Well, how do I keep track of all of these connections? How do I actually do the loops to do all the sums of everything? And how do I read the outputs? I'm going to get to all that. But this is the overall structure. So let's go back to the code. And now let's actually try to write a little bit of this library. Very, very little. So where am I going here? Okay, so this is my code. There's nothing yet. I'm going to create a new file, and I'm going to call this nn.js. So this is now going to be my... So here's the thing. Ultimately, I want this to be like a proper JavaScript library. But ultimately, what is a JavaScript library but a file with some JavaScript in it? So I might later, as this gets more sophisticated, optimize it and do some sort of build process or break it up into multiple files. But right now, I just want to kind of get the pieces going. So I'm also going to use ES5 syntax. This is the trajectory that I've been on. Soon in future videos, I'm going to start adopting some ES6 syntax. But ultimately, maybe this library, I'll do a follow-up and come back and I'm going to do a lot of things, maybe not in the most optimal or efficient way, but hopefully in the most easy to understand and follow way. So I want to create a constructor function called neural network. Okay, and I should also mention again, while we're here, that I built this library already, and when I built it, I based just about everything out of this book called Make Your Own Neural Network by Tariq Rashid. And so while I'm doing this now kind of a bit more on the fly, I'm sure everything that's in my brain ultimately came from here, and probably some other sources too. Okay, so what do I want to do? The core thing that I want to do is I want to create the neural network with a certain number of input nodes, number hidden, number of output. So I'm going to add those as arguments here. I'm going to say number of input, number of hidden, number of output. I'm going to create a neural network with 3 arguments, and then I'm going to say input nodes, I think I'm going to be long-winded about this, equals number of input. And so I'm going to create 3 hidden nodes is this argument, and output nodes is this argument. Is that an O? Yes, it is. Okay, so this is, we've actually written some code. The idea being that what I want to do is say things like var brain, and brain is a new neural network that has 3 inputs with 3 hidden and 1 output, right? This is the idea. So I need to figure out what shape, and shape, using the word shape very specifically, does the data come in? That's how many input nodes I want. What shape is the output that I want? Am I looking for a single output? Am I trying to look for a range of outputs? That's how many outputs I want. Then how many hidden neurons do I want? Well, that's kind of an open question. Well, maybe I want as many as I could possibly fit in with the program running reasonably fast. But it sort of depends on the complexity of the problem, and we'll come back to that later. And I should also note that this is a oversimplification of how neural network architectures can be. This is by definition a 3-layer network. And this library is only going to allow for a 3-layer network. An input, a single hidden, and an output. But as something you might think about for the future, how would you write the code to have multiple hidden layers? Because a lot of neural network-based learning systems need multiple hidden layers to be able to perform optimally. But for now, I'm going to keep things very simple. Okay, what is the next step? We did write some code. Everyone thankfully wrote some code, but now we got to stop again. The next step is the feed forward process. The way that the feed forward process works is that we receive these inputs. Oh, there's so much to do. So many pieces to this puzzle. I'm excited to get through it all though. So let's just say, for example, we're looking at this hidden neuron. Do you remember from the Perceptron videos? Maybe you didn't watch those, so let's talk about it. The idea is that we need to do something called a weighted sum. So let's pretend this is the house prediction thing, and this was the number of bedrooms, 3, this is the number of bathrooms, this is the the square feet. So each one of these connections, right, the data is going to flow in. The data comes in here, the number 3 comes in here, and then look at this. There's 4 outgoing connections. Each one of those connections has a weight to it. Now, ultimately, the whole point of doing this neural network-based learning system is we want to tweak those weights. We want to train the brain, train the neural network to have optimal weights to get good results, results that make sense. And that training process is something that I'm going to get to. I don't know how many videos down the road from now, but not too far away. These weights will typically, to start, one way of thinking about them is they're going to just have random values between -1 and 1. And there's a wide variety of techniques and strategies for initializing random weights, or not just random, to a neural network. But for right now, a good way for us to get started is they all have random weights. So even though I'm looking at each one of these flowing out, a slightly better way for me to look at this with you is actually just to look at all the connections flowing in. So this particular hidden neuron has 3 connections flowing in. And the input values are 3, 2, and 1,000. Each one of those has a weight. So let's pretend this is like 0.5. Let's say this is like -0.5. And this particular weight is 1. So I'm making using very, very simple numbers. The idea is that each hidden neuron does something called a weighted sum. So it takes the input multiplied by the weight and adds that to the other input multiplied by the weight and adds that to the other input multiplied by the weight. So we could actually do this. 3 times 0.5 is 1.5 plus 2 times -0.5 is -1, plus 1,000 times 1 is plus 1,000. So this value now is 1,000.5. Now, we can see there's a huge flaw here, which is that the fact that square footage is kind of a big number and number of bedrooms and number of bathrooms are small numbers means this kind of way of summing it is going to produce some like odd results. The square footage is going to be weighted so heavily just by the fact that it's bigger numbers. So a lot of time in working with a machine learning or neural network based system, we need to do some type of cleaning or normalizing of the data, and we might do something where we sample this down so that we actually do the number of bedrooms between 0 and 5 as a value between 0 and 1, and number of bathrooms always as a value between 0 and 1, and square footage. This would actually turn into 0.1, like because the range is between 0 and 10,000 square feet or something. So we would do some kind of normalization of these values, but this is again further down the road when we start to apply the library in an actual project. Once this weighted sum is complete, the result of that weighted sum gets sent out through the outgoing connections, but it gets passed through an activation function. So I'm going to come back to the activation function. This is something we did with the Perceptron, and that's going to be a separate video where we look at different activation functions and how they work. Right now I want to focus on this weighted sum. So I could keep going here. I could create some type of array I could create an object that's like each one of these nodes or neurons is an object, and then I could iterate over, I could have connection objects. So there's a bunch of different approaches I could take. But the classic and standard approach is actually to look at storing all of these weighted connections in something called a matrix, which is really just like a spreadsheet, a grid of numbers, looking at the inputs as an array and doing some type of math that basically take that array of inputs, multiply it by that matrix of weights, and generate the outputs of this hidden layer. So give me a second here. I'm gonna make the case for this with a simpler scenario. So let's look at this diagram, which just has fewer connections. It's going to be easier for us to unpack. So we can think of these inputs as x0 and x1. Let's not even worry about the output right now. These are the inputs. This is the hidden layer, right? Hidden layer. So let's think about this. And actually, let me change these numbers to x1 and x2. Sometimes I like to count from 0, sometimes I like to count from 1. I don't know why, but I feel like in this case, let's call it 1 and 2. So this is really like hidden 1, hidden 2. So each one of these connections, right, each one of these weights, you could say here, this is a weight that goes from 1 to 1. This is a weight that goes from 1 to 2. This is a weight that goes from 2 to 1. And this is a weight right here that goes from 2 to 2. So notice how there are 2 inputs, 2 hidden neurons, 4 weights. In other words, the weights, I'm going to kind of start to use matrix notation a little bit. The weights can be expressed like this: 1, 1, 1, 2, 2, 1, 2, 2. Okay, so this is a way of expressing the weights. And a way of expressing the inputs, I could write it like this: x1, x2. Okay, so I'm making the case that I have 2 inputs and I have 4 weights, and I could write it out like a matrix of numbers, a 2 by 2 matrix. And this is essentially a 2 by 1 matrix. Whenever I'm going to get more into matrices in the next video, or am I in that video already? I don't even remember. I don't know where I am in my world. But typically, when we talk about a matrix, a grid of numbers, we reference it rows by columns. 2 by 2, 2 by 1. Okay, so let me just show you something. Remember this? We need a weighted sum here. This weighted sum is x1 times weight 1, 1 plus x2 times weight 2, 1. Okay? That's the weighted sum for this neuron, or node. The weighted sum for this neuron, or node, is x1 times the weight from 1 to 2, and x2 times the weight of 2 to 2, plus x2 times the weight of 2 to 2. It so happens, I could take these 2 results, I could call this like H1 and call this H2. And I could say, let me actually say, I could basically say this times this equals H1, H2. So this is the actual math, the way that we described it. Look at both inputs coming in, multiplied by their weights and summed. Look at both inputs coming in, multiplied by their weights and summed. These are it written out. But it so just happens that this exact math, writing it like this and producing this outcome, is exactly the math that is part of a field of study called linear algebra. Linear algebra involves manipulating vectors and matrices. A vector being a one-dimensional list of values, a matrix being a two-dimensional list of values. The inputs are always one-dimensional, the outputs are always one-dimensional, the weights can always be expressed as two-dimensional. It's every input connected to every hidden. You can think of it very much like pixels, every row and every column. So this is where I need to stop, and what I want to do is do a few videos that cover this notation and math with a bit more detail, writing a little JavaScript, simple JavaScript matrix library. And ultimately, once we've done that, we can come back here and see how if we have that library written, we can then use it to do the math between the inputs and the hiddens to the output. And ultimately later, we're also going to go backwards through the network to tweak values and train it, and we're also going to use the same matrix math. So this is why we need, or why we don't need, because we can kind of do it without it, but why it's useful to work with this idea of linear algebra. And I should note, once again, that if we were doing this in something like Python, using a library like something called NumPy, we would get all of this stuff for free, and there are JavaScript matrix libraries, but I'm going to kind of unpack some of this and write a lot of the code from scratch just to have a sense of how it's working. So hopefully as you were watching the video, you saw a little annotation. This is actually incorrect. I mean, everything about this math is correct. This matches this, right? The weighted sum is x1 times weight 1 from 1 to 1, x2 times weight from 2 to 1. But actually the notation the way I wrote this matrix, as I go into the next video where I actually look at how the matrix math works, this really should be written as 1, 2, and this should really be written as 2, 1. The reason why that is this should be x1 times w11 plus x2 times w21, which is written right here. So that matrix math that I'm going to go in more detail in the next video, we take this row and multiply it by this column, and this row and multiply it by this column, and you can see that's what these two things are. Okay, so thanks for bearing with me. There's a lot of little pieces, but I am going to get back into the code. So in the next video, I'm not very confident about the order I'm doing all this in, but it's just the way that I'm going to choose to build it. And so in the next, again, I'm saying this again, the next video, I'm going to look at the matrix math again and then write a generic library that does that math and then come back and put it back into the neural network itself. Okay, so see you in the next video. Thanks.